But before we get on to um, the proper definition of the Taylor polynomial, we have to introduce some notation, right? So we've been talking about negligible sequences before, functions or equivalent, asymptotic equivalences, things like that, right? But in order to explore this in more depth, and we will need more depth, in order to express the Taylor polynomials, we need to introduce more formal notation, okay? And this is what's called Landau's O notation, okay? The O notation, the small o. Okay, so coming back to our definition of negligible function, so f is negligible with respect to g when x goes to a, right? And a can be any number, including plus and minus infinity, if the limit when x goes to a of f divided by g is 0, right? So this is equivalent to the definition we had for sequences, right? Now the new thing is that now if f is negligible with respect to g when x goes to a, we write it like this, okay? And we read it: f is small o of g as x goes to a, okay? So that's going to be important, right? Let me first give you an intuitive understanding of this, then we'll go on to some properties and then some examples, right? So the idea here is that when we go to x goes to a, right, the value of f is very small when compared to the value of g, right? So if you think about, the limit when x goes to 0, a function f that, for instance, goes to 0 much faster than function g will be small o of g, okay? But we'll see some examples later, right? Okay, so there's a set of basic properties that are make this notation very useful to work with, and that's why we use them, right? And so there are 5 of them, and will be very similar to other properties that we've seen before. So for instance, that the first one is that the small o scales, right? So if we have f is small o of g when x goes to a, and we have a lambda, a real number, lambda, then lambda times f is also small o of g, okay? And the proof of this is easy, because if f is small o of g, then we have that the limit when x goes to a of f divided by g is going to be 0, right? But then if we multiply f by lambda, right, we multiply this by lambda, then this is still 0, right? Because the fact that we have multiplied this limit by a number doesn't change anything, right? Okay, so that's the first property. Let me think. Now, the second property is that this small o is additive, right? So if you have f1 and f2 are both small o of g as x goes to a, then the sum of them will also be small o of g, okay? So that means that if f1 and f2 are small o of g, that means that the limit when x goes to a of both of them divided by g, right, is 0. But now if we combine these two things, we have the limit when x goes to a of f1 plus f2 at x, right, divided by g. This is the same as the limit when x goes to a of f1 at x divided by g plus the limit when x goes to a of f2 divided by g. But this thing is 0, this thing is 0, so the sum is 0. Okay? So f1 plus f2 is small o of g as well. Now, if we have that f1 is small o of g1, right? Let's see this, and f2 is small o of g2, then the product of f1 and f2 is small o of the product of g1 and g2. Okay? And you see the idea here. We have we need to check that the limit of this product f1 f2 divided by the product of g1 g2 is going to be 0, right? But we have the limit of this is going to be 0, the limit of this is going to be 0, so all of this is going to be 0, right? Now the transitive property is that if we have a function f that is small o of g, okay, this is equal to 0, and then the function g is small o of another function h, okay, so these two limits are 0, then f is smaller of h, okay? So we need to prove that the limit when x goes to a of f divided by h is 0, but then if we multiply and divide this by g, right? Multiply and divide by g, again we have this limit is going to be 0, and this limit is going to be 0, so all of this is going to be 0, right? So f is smaller of h. And then finally we have the factorization property, right? So we have that f is smaller of g, so the limit when x goes to a of f divided by g is 0. And then we have that we want to prove that the limit when x goes to a of h f, okay, x divided by h g at x is going to be 0, right? But we can factorize and express this like this: h at x, f at x, h at x, g at x, right? And then h and h cancel out, and you have f divided by g, but we know that that limit is going to 0. Okay? So all of this, maybe this is very abstract, as we have been saying so far, but we have a very shorthand version of these properties that maybe it's helpful. Okay, so we have small of g multiplied by lambda is small of g, right? Small of g plus small of g is small of g. Small of g1 times small of g2 is small of g1 times g2. Small of small of h is small of h, and h times small of a of g is a0 times, h times small of g is small of h times g. Okay, so these are the common multiplications, manipulations of the small o symbol that we will use over and over again, right? And so we'll leave them here while we work on our examples, right?